Okay, it's my pleasure to introduce Zhi-Zhen Wang, who will tell us about analytic continuation of one-loop amplitude and its evaluations. So please, Zhi-Zhen.
Yeah, thank you. Thank you for the opportunity to be invited to IMSA for this online talk for our recent work, based on our recent paper with my supervisor, Professor Yamaho. I mainly talk about the string, how to evaluate the one string amplitude. Today, this talk will be split into 5 parts. I will first give an introductory about why we're curious about the string amplitudes and how we define it, and then specifically I will focus on the one string amplitude that will be our main examples today, and I will introduce a string theoretical analog of the I epsilon prescription for how to evaluate, and give a first toy example for the bosonic open string and introduce the first method by integrating over the Rademacher contour to obtain the evaluation of the one string amplitude. And then I will introduce two new approaches for via analytic continuation to also evaluate the one string amplitude for various examples. For example, the one open for bosonic or type 1 or other kind of a superstring, and also for the closed string. So I will first introduce why we care about the string amplitude. Since 1968, Veneziano wrote down a formula for the tree level string amplitude. It has played an important role in the string perturbation theory. We care about the string perturbation theory because not like in quantum field theory, in string theory, we don't have a well-defined version of its non-perturbative version. For example, the M theory or even the F theory. But 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 we can do it in a perturbative way by treating it as matrix analog, like in quantum field theory. So the amplitudes and the S matrix in string theory, how to define it, it is very important for us to encode the low energy interactions, and also the best playground for us to test the string dualities and the underlying symmetries, etc. Another motivation for us is that it's also a rich source for inspiring some other fields and the interconnections. For example, the double copy relation, or also known as the KLT relation, which states that the square of the gauge theory amplitudes is equivalent to be a gravity amplitude, and also some mathematical relations, for example, the algebraic geometry and also the number theory, etc. Actually, today our technique will borrow some ideas from the number theoretical way based on the modularity. That's our main technique we will use. And in one word, if you are not familiar with the string perturbation theory, the string perturbation theory is to argue that we want to integrate the SCFT or STFT correlators on the modular space of the Riemann surface of genus G or and puncture N. I will give a more give a clarification for this sentence. So in general, we have a string amplitude is given by this path integral based on the Polyakov action and an integral over the embedding field X. It can be commutative or non-commutative based on your bosonic or fermionic degrees of freedom. You can insert it, and the word to the metric gamma. And we have some degrees of freedom of fixing the gauge. So we need to divide it by the volume of the gauge groups. And in this action, this integral is taken over the worldsheet with your desired asymptotic states, like in scattering amplitudes. The asymptotic states are on the boundaries of the worldsheet, and in order to compute it, you need to use the conformal symmetry to pull the infinite stretches of the worldsheet back to the compact surface at the center. Then you replace this asymptotic states by inserting some appropriate operators on the worldsheet. These are known as the vertex operator insertions. This can also be treated in a CFT way by state operator correspondence. And it then the integral over the x becomes a CFT creator on the worksheet, and by fixing the gauge, you will cancel the volume of the you'll cancel the volume of the gauge groups, and may introduce some ghost fields, and the integral over the model. The integral becomes an integral over the modular space of the Riemann surface with the point insertions that carries the kinematic information from the external states, and it can be expanded in terms of this in terms of its genre, and in terms of this string coupling constant. But today we will mainly focus on the case that we have fixed the GS equals 1, and also the alpha prime is also finite. More specifically, if you have fixed your gauge, you get some ghost fields, and you get a series of vertex operator insertions in this correlator, and you do the integral over the modular space of Riemann surface Riemann surface of genus G and puncture N that parameterized by a complex structure moduli tau or tau bar. In presence of tau bar, it means you are considering the closest string. Like these graphs are these topologies are corresponding to the wordsheet that's swapped by the closest string. If it's an open string, you will get some just a sphere and some a cylinder in one loop. Any questions to here? Okay, and so there are some typical examples that we have been familiar with. For example, the tree at the tree level, we have been familiar with it since 1968. This is just an integral over a sphere. We have obtained a compact formula for this for this kind of integral. And we have a generic way which is known as the pure spin formalism. We call this formalism because this will tell you how to fix a gauge and cancel all the ghosts, all the ghost numbers, ghost fields. The pure spin is similar to the MHV the helicity method in the amplitude, so that you can fix all the external states as massless degrees of freedom, and then you can write down a compact form. And also the KRT relation at the tree level is also well known for the tree level open string and closed string, or the gauge field theory amplitudes, and the tree level open string amplitudes. And our focus today will be the one loop string amplitude. When you go to one loop, the modular space, you can see the topology is given by these by a torus or a cylinder, depending on you considering the closed string or the open string, and it's on a random spot. For example, the movie strip. There are some examples that have been investigated. For example, the type 2B. Or even for heterotic string, it has been considered in the low energy expansion when you expand over alpha prime, when you consider alpha prime goes to zero limit, you can do some supergravity approximation to do this calculation. But there are still a lot of examples that are still unknown because of the presence of the singularities and cusps in the modular space. We will see that, and that would be our main focus to tell you how to treat the integral over this modular space. Another thing to note is that the KRT relation for the at one loop is not so clear that we know there exists a KRT relation at one loop for the open string and the gauge and the field theoretic amplitude in, for example, the Yam theory, but we have no clue what kind of exact relation between the one loop open and one loop closed strings. And our evaluation may give a clue how the integrand are connected to each other at one loop open and one loop closed string. Up to here, any questions?
Probably
Okay.
not so far.
Yeah. And I will just go into some details about the one loop string. So as we have discussed, these string amplitudes can be given by this integral over a certain topology. For example, the open string, the one open string is just given by the cylinder and its Mobius strip, the unrounded counterpart. For the closed string, you consider the torus in the bulk and the cylinder Mobius strip and the Klein bottle on the boundaries. And if the insertions are on the different boundaries, you will get a nonplanar part. You will get a nonplanar diagram, and you need to consider an additional contribution from the nonplanar part. But the treatment for the nonplanar and planar part are basically the same. So we will only discuss the planar parts today for an illustration. Specifically, a generic open string is given in this way with the integrand f, a holomorphic modular form that have been investigated by mathematicians that can be written as a certain modular object known as the elliptic multiple zeta values. This is an integral over the configuration space coordinates and over the Kobayashi factor, which accounts for how you determine the Chern pattern factors in the normal string amplitudes. And you need to integrate and the modular space, which is a modular curve here, integrate over this gamma e, which is depicted here by when tau equals 0. When tau equals 0, you identified the z and z plus iy, which accounts for the cylinder topology. And when you have z identified with the z plus 1 over 2 plus iy, you have the topology of the Mobius strip and with the reversed orientation. And this gamma e denotes how you integrate over the one of open string amplitude. And specifically, we are curious about how to do the integration over the d tau part because we have seen that the mathematicians have given a generic way for how to determine this f by integrating over the dz, but you can see that in the tau space there indeed exists some singularities at uv and even at IR for near tau equals 0 and tau equals 1 over 2. We will go into details later that near this point the integral will be divergent and we need some further process to treat this integral. Similar thing happens for the one closer string. In open one closer string for closer string, the integrand again has this non-holomorphic modular form has also been shown to be a certain modular form known as the modular graph form, but because of the integration domain now is just the fundamental domain on the upper half plane, we again need to treat the singularity at the tau equals I infinity. This will be our key technology to do this integral. So you can see that it's clear that near the infinity you will have some singularities. You have some UV singularities that makes your integral diverge. And specifically for the one of open string near tau equals 0 and tau equals 1 over 2, they break the modularity when you take the tau goes to minus 1 over tau. If you do that transformation, you will see that both modularities near the tau equals 0 and tau equals 1 or 2 will be is violated. So we must do something to treat these IR singularities and due to the existence of the tachyon divergences, we also expect that there indeed have some tachyon divergences some IR divergences near tau equals 0 and tau equals 1 over 2 for the one of open bosonic strings. For example, for the bosonic strings, these are some typical examples in the Patinsky. And the answer to treat this integral over this modular contour or the modular domain is to use the analytic continuation. We will show a string theoretic analog way similar to the quantum field theory to circumvent these singularities at the 0 and 1 over 2. And also we will give to circumvent the singularities at infinity. Do you hear any questions? Okay. Yeah, then I will firstly give a crash course for why how we define the Euclidean and Lorentz, how I introduce the Euclidean and Lorentz signature in the quantum field theory. As we are familiar with that the Euclidean integral, the Euclidean propagator this integral is convergent when you have p squared plus m squared larger than 0. And when you introduce the I epsilon prescription and change it to the Lorentzian time, you have an integral that is oscillatory. And but because of the convergence factor that's given by the TL times the minus TL times epsilon for infinitesimal epsilon, you will get this this oscillatory convergent this oscillatory integral to be convergent give a proper treatment for this time ordered correlation function. Typically, in string theory, we can do the same thing, but in string theory, we are always treating the Euclidean signature, and it's equivalent to say you are integrating over the modular space of the Euclidean word-to geometries. This is where the tension comes. The fact is that you can look at this graph. So you are actually integrating over the Euclidean wordsheet, but in the Lorentzian signature. In the region of the modular space that where the Riemann surface develops a long tube, this long tube originally, if you don't introduce the I epsilon prescription, this long throat will be controlled by will be parameterized by E2 minus TE, because when you were in the Euclidean signature. And it's clear that when you have large enough Euclidean time, this E2 minus TE will make this wordsheet degenerate. So we need so in this region of the modular space we need a proper treatment for this throat part, and the natural idea is just to apply the weak rotation from the Euclidean signature to the Lorentzian signature near this degenerate region. So we just use the reparameterization by complexification by identify this a complexified Schwinger parameter as TE plus ITL. So that the degenerate wordsheet could have a well-defined way to have an integral to convergent. To make this more explicit, we can see this graph. We can see at the t-plane, at first we are integrating over the Euclidean time up to a very large value t0, beyond which the Euclidean integral will be divergent and the wordsheet becomes degenerate. And after that, we apply the weak rotation so that we change the Euclidean time to the Lorentzian time, and the path integral continues vertically along the imaginary Lorentzian time. And combinedly, this T is defined as a complexification of the Euclidean time and the Lorentzian time. And in the right panel, this is just another parameterization when you define the Qx minus E2 minus T, which parameterizes how the word should degenerated. Like we firstly move inward, and up to a very small fixed radius, we have an infinite spiral that move radially inward around the Qx 0, but never goes to Qx 0. This is where the long tube becomes long enough that breaks the Euclidean signature at the normal region.
Sorry, Zhi-Zhen, there is a question from
Yeah.
Shell.
What dictates the value of T0? T0? Is it determined by the physical parameters of the theory?
Okay, that's a good question. So this T0 it 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 ac- it depends on whether you're just when you implement the IEPSLN prescription, you expect that there exists a convergence factor that makes your integral makes your Lorentzian integral to be convergent. So you need to guarantee that this T0 is large enough to get the T0 to minus S to make this integral to be convergent. This is how you get this T0. Does it?
Okay.
Yeah.
Thanks.
Yeah, and I will show you that the specific choice of T0 that doesn't really matter when you evaluate the string amplitude, because we expect that our theory doesn't have any is not controlled by a specific variable. But this T0 indeed it would matter when you introduce it to get this IEPSLN prescription to be well defined. Thanks for the question. Yeah, so after this weak rotation, we have this long tube to be we have this long tube that may degenerate on the worksheet to be convergent in the Lorentzian time. And for the case that we will consider, this convergence factor is given by this this T2 minus S, where T is just the complexified Schwinger parameter given by TL plus ITE. And this is always true when for the cases that we will consider for the string amplitudes, because this S is always larger than 1, which means the weight of the string amplitude will always be less than 1. This is the case that we will consider. Any other questions? Okay. This is just to quote. This is firstly introduced. This picture is firstly introduced by Witten, and it was recently, after 10 years of Witten's paper, was firstly applied to evaluate the one-up string amplitude by Eberhard and Misera, which is also the work that inspiring our further development. And so I will firstly introduce a toy example for the one of the bosonic open string. We recall this. We have a generic way to evaluate this amplitude, but we don't know how to do the integral over the gamma e. For bosonic open string, and we now consider for simplicity we consider no insertion. We just consider the integral over this cylinder topology without any external states. So we just receive contributions from the 24 from all the tachyons. So you have the 1/eta 224. For your intuition, these are just the model functions, the dedicated eta function and some Jacobi's seed functions that we will use later. And after the weak rotation, the most difference is regarding this gamma e to gamma 1 union gamma 2. For your impression, this gamma e are approaching the target 0 and target 1 or 2 infrared limits at from the top. But after the weak rotation, we have a reparameterization which tunes a bulb that approaching the target 0 and target 1 or 2 from the right rather than top. And they are not touching the target 0 and target 1 or 2 singularities. By identifying this 2 pi I over tau and the complexified Schwinger parameter T0 plus IT. Then we have this as we have introduced this reparameterization in the Lorentzian time makes this bulbs near the target 0 and target 1 or 2 to have a convergent integral. So this integral over the gamma 1 union gamma 2 is kind of well defined, but we need a further process to extract the UV singularity. We showed that we can show that for there exists cutoff capital Y. We divided the UV singularities into the integration over the small gamma y, and this integral is only depend on the derivative of the tree level amplitude, So the one loop string amplitude for the bosonic open string only depends on the integral over the capital gamma y. We only need to care about in the I epsilon prescription. We only need to care about how to treat this kind of integral. This is a graph from the from Ephard and Mizra's work. So for tau equals 0 and tau equals 1/2 and tau equals I infinity, all three singularities can be treated by integral over this capital gamma and divided into divide the tau equals I infinity limit to be wrapped by the integral over the small gamma. So we only need to care about how to treat this how to treat the integral over this capital gamma. We will see in our approach in our new approaches we can actually directly treat this integral. But I will first introduce how Ephard and Mizra firstly evaluated this case because they introduced the first method that is a bit magical in the first sense. They introduced a way to integral over the Rademacher method for a detour. This Rademacher contour is defined as it wraps over all the circles that touching the real line at all the rational fractions at this rational fractions d over c. For the ABCD are the components of the SL2, Z. And you can see as a detour, this integral over the gamma infinity is just the equivalent to say you are summing over all the residues at all the rational fractions between 0 and 1/2. Between 0 and 1/2 for A over C. And what Ephard and Mizra firstly done is they showed that the integral over the capital gamma is just the equivalent to be the integral over the Rademacher contour gamma infinity. So this part of the integral is just given by it's simply given by all the by summing all the residues at the fractional numbers from 0 to 1/2. Then they obtain the result by with a rapidly convergent sum by and give a first evaluation for the one bosonic open string and with a complex evaluation. Note that if you always use the first pass integral that I introduced in the first few slides, you are always without any I epsilon prescription, you are always treating an integral that is a real measure, and you can only get the real value of the integral of the integration, but which loses a lot of information because you know that from the optical theorem you expect that the imaginary part of the amplitude accounts for the unitarity and also the decay width of a scattering process. Up to here, any questions? Okay, so this is the first approach and the first example that is just given by Ephard and Mizra, and we will introduce two new methods to treat this. To firstly we can recover their result, but also we can fix some issues that by just integrating over the Rademacher contour that cannot done. The point that you may have noticed is that you can replace the integral over the capital gamma by the Rademacher contour. Only it is because you are treating the open string amplitudes. You only need to care about the open modular space in terms of a single holomorphic parameter tau. But when you treat the closer string amplitude, you need to consider a domain that's given by d tau wedge d tau bar, right? Then it's not sufficient to just use to simply replace the modular contour by a one-dimensional contour by any one-dimensional contour. You need to introduce the I epsilon prescription to define a new integration cycle that is two-dimensional in the fundamental domain. for the closed string. And we will see how to do this. Firstly, yeah. Any question? Okay. So recall the closed string amplitude. We have a generic form for non-homomorphic model form times imaginary part tau, which the y denotes the imaginary part tau to some power. Specifically for the closed string amplitude without insertions, it's just a model square of the eta to 24 and with some y. And we indeed have a lot of experience from the number theoretical way, from the number series that on this kind of a modular integral. Let's show how we use this way to introduce the I epsilon to introduce the I epsilon prescription for the fundamental domain. Firstly, we should give a complexification of the modular space, because we are considering an integral in a new cycle, the Fi epsilon in the complexified upper half plane for H and H cross H tilde, where H tilde has the opposite complex structure to H. This is a real when we introduce the I epsilon prescription, this is a complexified upper half plane that you need to consider. And we firstly introduce a cutoff y for the fundamental limit to make it more explicit. We first introduce a cutoff y for the fundamental domain, where it decomposes into a finite region Fy and a semi-infinite strip that captures the singularity at tau equals I infinity, right? As this denotes. And we can show that there exists an embedding from this Fy to the complexified upper half plane by identifying Z and Z bar, where Z bar is just the coordinates parameterizing the opposite complex structure space. Similarly, for the Sy for the semi-infinite strip, we can do the similar reparameterization in terms of Z and Z bar, so that we can define this Sy in the H cross H tilde. Then we define a new integration cycle by introducing the I epsilon prescription by union the Ft0 and St0. Here we have identified this y equals this cutoff y as T0. Any questions to here? Okay. Yeah, then we can just do the integral over this Fi epsilon and parameterize the 1 over eta to 48 in terms of this tau and tau tilde. And this has a nice Fourier expansion with this amount L has been known from the number number series that is given in this integral that you can treat term by term for the Q series. So you only need to expand the modular functions in terms of Q series and do the integral for the Q series term by term to get a finite result. And we indeed can do the evaluation and obtain the finite result for this one bosonic closed string without any insertions. Another approach is just to forget all the things that we have introduced for the I epsilon prescription. We can just because there only exists I epsilon I infinity singularity. It's also natural for our physicists to do the regularization directly. We actually can introduce the cutoff y and take a limit y goes to infinity to recover this fundamental domain, which is only diverged when m plus n is less than 0, which means where the polar terms manifest. And this can be done in terms of when we expressed it in terms of the generalized exponential integral, the ES. This finally, when you take y goes to infinity, you can write down a formula like this, which is similar to the case that you have seen in the first approach by introducing the I epsilon prescription with just a minor difference in the second term. You can see that this is the right hand side is definitely finite because the first term is just an integral of a finite region, this purple region, and the next term is only non-vanishing when the power of q and q bar, m and n, is equivalent. And the generalized exponential integral, we also have a definition. It serves as the complexification of the normal exponential integral by identifying the s equals 1, as you can see. And this indeed have a finite evaluation. So, and this is the way that the number theorists have done to do the regularization of the fundamental domain. So you can do, in principle, you can do any integral over the fundamental domain in this way by regularization to reproduce a finite result. And of course, as expected, if you just do this evaluation, put this data into your Mathematica, you will get the same value as before, as the first approach. A comment about this generalized exponential integral is firstly for non-integer s, for this weight, we fix the branch by specifying the argument in the minus pi to pi, and for the argument is a negative number, we choose the integration contour not through the upper half plane but on the lower half plane. This is a bit different to normal conventions, but this will give us a nice formula for the give a nice analytic formula for the imaginary part of the generalized exponential integral. This will play an important role when we evaluating the imaginary part of the string amplitudes. So the equivalence of the two approaches is just given by the equivalence of this 2L in the regularization regime and by introducing the I epsilon prescription. They are in the complex plane by some complex analysis exercises. You can easily show that they are equivalent by showing this identity. This is very easy to show if you put these two integrands on the complex plane and take the t0 to consider t0 is a very large limit and consider this the left hand side and the right hand side are on the infinite radius circle on the complex plane. So these two approaches are actually equivalent, and we will see some examples later. Firstly, we consider the bosonic closed string case that is untreatable by Eberhard and Miseras work. In our way, we have known the integrand for y2 minus 14 times eta tau to 48. So we have a weight minus 12, and the s is just 14. Then inserting it into the L into the epsilon, we have this formula in terms of the generalized exponential integral and the Fourier coefficients. And by summing over it, you get a finite value. And recall that the imaginary part of the exponential integral is given in this form. You can see that the imaginary part of the amplitude, which is just equivalent to be the imaginary part of the E14, with some prefactors, and then you get a closed analytic form for the imaginary part of the one closed string amplitude without any insertions. In this way, this is the kind of the first time that we have reproduced an imaginary part of the closed string amplitude, the bosonic closed string amplitude, and give an analytic form for its imaginary part. And this I will show that this imaginary part indeed confirms the unitarity, especially and can reproduce the Reg limit. Any questions to here? Okay. Yeah, generically, you can also write down.
Sorry, just one question. I think I'm just missing something. So in QFT, if you have one loop amplitudes, you
Yeah.
would expect to see some analytic structure, including branch points and um, in the complex plane. Where do you see that here?
For string amplitude, I think the thing is a bit different. That the first thing is that I should consider that we know very little about because we know very little about the physical implication of the one string amplitude. That especially it's a unitarity based on this imaginary part. But the only thing that we can confirm is that. We want to by taking the Raj limit, by taking the Mandelstam variable s goes to infinity in the high energy limit, you expect that your amplitude will reproduce your imaginary part of the amplitude will reproduce your the Raj limit, the Raj trajectory. That's the thing that I know. Yeah.
So if you take the sigma parameter to 0, so on the world sheet, if you uh, essentially take a very thin world sheet, then you're kind of coming back to a point particle limit of the computation. Maybe in that limit, one can see if what kind of analytic structure there is.
I see. Yeah, for I may introduce some cases that are more relevant to that because now we are only considering considering the amplitude the examples that without the insertions, right? These are just some vacuum amplitude that receives, for example, the bosonic case just receives all the tachyon contributions that shows why there are how to evaluate these tachyon divergences and how we cancel them, right? But for the point scattering that if you want to compare it to the quantum field theory, for the point scattering or that is more relevant when you consider some insertions. Is yeah. I was showing example later. Thank you for your question. Any other questions? Okay. Yeah, so generically we can write this form for modular integral in this way because this is something that usually treated in the in the number theoretic way. And then we come back to the one of open string amplitude. We again introduce a cutoff, and we can again but because of the presence of the singularities at target 0 and targets 1 or 2, we need some further steps to do some model transformation to move it inside a contour that has no singularities. The basic idea is just to do the transformation near the target 0 and targets 1 or 2 to keep the modularity. And expanding them in terms of the Fourier coefficients. Specifically, the integral over the capital gamma by direct integration, you can find that it receives two contributions from the semicircles, from the two semicircles, where the curly arrow is just denote the reverse orientation for this -1 to L, and the integration for these two semicircles are just interpreted by this generalized exponential integral, and the integral over the vertical and horizontal lines, horizontal segments, just gives you a horizontal f0 and the sum of the exponential integral of the exponentials. And they only depend on one single parameter, that is similar to the temperature variable by 2 pi over T0, where T0 is very large. And note that this horizontal part only contribute when you have a integer m. And then by summing over them, you can just obtain a finite a generic analytic formula for this integral over the f tau in terms of the generalized exponential integral and the Fourier coefficient. And you can evaluate it's a real part that corresponds because the amplitude is just minus I. The amplitude is minus I times this integral. So the imagined part of the amplitude corresponds to this real part of this integral. That is just that again has an analytical closed form. I say closed because the polar term which means the n is the term that with n is negative is always finite. And note that even though each individual term depends on the choice of T0, we can show that when you sum these three terms, when you sum these three terms up, you can show that its derivative in terms of the T0 is just vanishing, which means it doesn't depend on the sum of them doesn't depend on this T0. And if you do the regularization you can do the same thing for the integration, like what you have done for the fundamental domain for tau equals I infinity limit. You can show that this integral over this small gamma is just minus one.
Zhi-Zhen, you mean the H term has dependence, but they sum up such that T0 dependence cancels.
Yeah, exactly.
Okay, so the whole gamma over T0 integral does not have T0 dependence.
Yeah, exactly. This is also we expected because you see that this T0 serves as a in this regularization regime, it serves as the regularization parameter. You
sure.
definitely
exactly, yeah,
definitely. Yeah, and you see that the horizontal constant term of the Fourier coefficient actually just canceled when you combine the capital gamma and small gamma integrations. That's also expected that the full integral, the full open string amplitude only depends on this generalized exponential integrals. Then we can try to recover what Eberhard and Miser has done. We again do the we first do the modular transformation at tau equals I infinity. We have a normal expansion for the 1 over 24, and near tau equals 0, we found that by taking the tau 2 minus 1 over tau 1, the Fourier expansion is the same, but the subtlety happens when you go to tau equals 1 over 2. In this case, you have a different expansion with a polar term at starts from the minus quarter, and the Monte function is given in this way, but the Fourier coefficient can be related to the normal Fourier coefficient of the 1 over 24 in this way. So universally, in terms of this f infinity, you can write it down in formula in this way. This is just the result for the one bosonic open string without any insertions. Although this looks very different to Eberhard's result, but they indeed reproduce exactly the same numerical result. At least for 11 digits. For the first 11 digits, we have confirmed our numerics. And another thing is that a further step of us is that we can treat the analytic form of the imaginary part. In this sense, it gives you a thing that not only depends on some constant and the gamma function, but also a z function. This is relevant for a sum that is similar to Eberhard's sum that obtained by summing over all the residues at the off fractional numbers. This is also known as a partial Kloosterman sum. I may talk it a bit later. I may talk it if time permits, but this is not this is go into too technical details. What we need to know is just this. We can reproduce this imaginary part of the the analytic form of the imaginary part of the one bosonic open string. With some remarks that you can directly do, for that direct integration, you are equivalent to say you are equivalent to show this identity, and we of course, as expected, we have confirmed all the digits at least to 11 digits. We have confirmed that matches the method by integrate over the Rademacher contour with our new methods. And one thing I should also quote is that also in this case, in this one bosonic open string case, the Ephort's method have faster convergence. The integral over the Rademacher contour will converge very slow, and it takes more time to get the result when you put it into Mathematica. But ours only take a few minutes, a few seconds to reproduce the same numeric. And one other thing one should note is the relation between the regularized domain and the domain with the I-epsilon prescription. If you directly do the regularization for this gamma e, for this Euclidean gamma that without any I-epsilon prescription, you actually can get this exactly same result, but with a minor change with the T0 to T0 to the just a change, just act as duality between the T0 and the 2 pi over T0. This just shows that the amplitudes after I-epsilon prescription, the amplitudes is equivalent to the regularized amplitudes with the over the contour that without I-epsilon prescription. This also confirms our expectation that these two methods are just the same, but in the sense that there exists a duality between T0 and between these variables. And the last but not least thing is that although we have showed that the sum that is independent to T0, the actual precise when you put it in Mathematica, because of still need careful treatment for the choice of T0, because the converging speed in the converging speed you can see it controls the converging speed for the exponential and also the Fourier coefficients for this term. So you still when we put it into the Mathematica to get the finite result, you still need to be careful about how to choose an appropriate T0 to guarantee the Mathematica to give you a finite value in an acceptable time acceptable time processing time. Any questions to here? Time. I guess I don't have too many times. I will first skip to the 2-point case that we have just I have just mentioned that may more relevant to the physics, because for the 2-point case we have a half integer weight, and one should note that if you use the Ephort and Mizra's work to treat this amplitude, you will get like about 1 hour's running time in your Mathematica. But for our method, we just need like no more than 30 minutes, no more than 30 seconds to reproduce the finite digits up to 10 digits. The point is that for 2-point you need to further introduce the existence of z. You need to fix it here. We fix it z0 equals 0 and z1 equals 1, so that we need to the amplitude is given by integral over z for this theta 1 over eta cube to some power that this power is just this power is determined by this the Mandelstam variable where we fix as Wang for intuition here. But you can do the same thing for other kind of modular functions, and this gives you a theta2 of 2 tau divided by e to the 6, and we again do the modular transformation at target 0 and targets 1 or 2, which gives you different kinds of modular functions and different modular expansions that has different product terms, start from -1/4, -1/6, -1/16. And again you get a finite result, and you have a imaginary part of the 2-point amplitude, and this imaginary 2-point amplitude is relevant to the case that you have zero thresholds when n1 n2 is 0 for this, which just corresponds to this blue part. And you can see if you do the evaluation for the higher S and the higher thresholds, you can reproduce this black red trajectory. And something more relevant to the physics is that this 2-point amplitude, you can understand it as when on the worldsheet topology, you have this a 4-point amplitude can reproduce our result when you take a double degeneration limit, when you take the 1, 2, and 3, 4 part very far apart to each other, then the 1, 2, and 3, 4 respectively identified and can be understood as a 2-point amplitude with a long throat in the middle where the Lorentzian time manifests. That is a bit more relevant to your previous questions, that actually the particle scattering.
Yeah, thanks.
Thank you. Yeah, and I should consider that I don't know too much about how to do yet to understand the physical implications that relevant to the string that can interpret this as string scattering and the in terms of the particle scattering. I think that if you are interested, I think some paper in 2016 by Ashok Sen. They used string field series viewpoint to discuss how the string vertex, if for example some cubic interactions, how this can be interpreted as how the particle scattering in the physical amplitudes to be connected.
Thanks.
Yeah, as a summary, we give a general strategy for evaluating this one open string and one closed string. Firstly we should determine the holomorphic modular form f tau, the integrand. This could be cumbersome for this modular transformation, but usually not hard for the open string amplitudes. You can also reproduce this integrand by double copy of the field theoretic amplitudes, and then you do the transformation, fully expanding it, and then integrate it over the analytically continued contour, this capital gamma, and then you just put your data into this formula and get it in mathematical, and you evaluate it, and you can evaluate it. For the closed strings, one of basically the basic strategy is the same, but it's more hard. It's much harder to get a finite form, to get a modular function expression or an analytic form for this non-holomorphic modular form f tau tau bar. But some physical hints from the KLT relation may help in this way. An example is a closed string 2-point. We don't know yet the relation between one closed and the open string amplitudes, but Stieberger recently have suggested that there exists an interpretation that you can write down the integrand of the one closed string in some of the modular square of the open string planar and non-planar integrands, which is given in this way for the planar. This is the planar parts, and this is the modular square of the non-planar parts. And in this way, we reproduce the for the first time we reproduce the one loop type 1 closed string 2-point amplitude with the analytic imaginary part. For this result we haven't found any other cross check, but this picture and this formula has been confirmed with by Stieberger's work. Yeah, and I think how many times do I have? I think I can stop here.
Still maybe a few minutes.
Okay, I can just give a final conclusion. Just we have provided 3 strategies to evaluate the one string amplitude. The first method is just a Rademacher contour by integrating over this magical contour, and you can replace this for the one open string amplitude. But for closed string amplitude, it's not good enough, and we introduced 2 new methods based on the IEPSON prescription and the regularize the fundamental domain. And we have showed that the latter 2 are rigorously equivalent on the in the complex analysis way, and they compared to the first method, they reproduce the same digits, numerical digits. And for the examples that we have shown here are just the bosonic and type 1, but but in terms of this Fourier coefficients and the generalized exponential integrals, up to we only consider up to 2 points, but we know that but our methods can reproduce the other types, like if you apply it to type 2a and 2b, it's also available. But if you want to apply it to heterotic string, it would be much harder to write it down because there will be a lot of variance when you do the model transformations, and it's much harder to get a finite sum in an acceptable processing time. And we have shown that there exists a closed analytic form for the imaginary part of the open and closed string. You can always use the imaginary part of the generalized exponential to reproduce this, and we found they recovers the retro trajectory in the high energy limit, and gives you a double degeneration limit of the most physical 4-point amplitude. The last thing is that what I should stress again is that although the choice of T0 is in principle independent, our evaluation is independent of the choice of T0, but in practice, because of the precision in these programmers, you still need to be careful about what kind of which T0 gives you the best convergence in an acceptable processing time. Yeah, I can stop here. Any questions?
Okay, let's first thank the speaker.
Thank you.
Let me see. Any questions? Let me check Zoom. Okay, Zhi-Zhen, maybe one precision from my side. When you do this squared computation of the closed string loop from the Stieberger's claim, do you think that there could be other possibility against how you could acquire these closed string integrals?
You mean
He's claiming this is not really a proof. I understand that you take this nonlinear part and you do the squares, but yeah.
You mean you want to find a new way to reproduce this modular integrals?
Yeah, or maybe from I mean from maybe from other method.
Yeah, the only thing that I know is just if you maybe you because actually let me back to
Hello, maybe you can get to the slide.
Yeah, I actually I'm quitting this slide Yeah, I come back to the
Especially, maybe you can also comment on this non-planar part, because I think you were mentioned your non-planar part was coming from when tau is 2 or something.
Yeah, exactly. But let me first give some comments about what you have just asked. Like for the the only method that I know is just you can use the string field theory to treat this integral. And previously we indeed have a string field theory interpretation for how to formally writing down this this kind of Euclidean path integral in terms of in terms of the string vertex and the BRST operators.
Yeah.
But yeah, that's the normal thing. But indeed, we don't have an interpretation for how to introduce the I epsilon prescription for that string field theoretical way. We don't know how to define we don't know how to formally define what is an I epsilon prescription and the corresponding Lorentzian propagator between the string vertex in the between the string vertices interactions in the string field theory language. That could be another way to reproduce to write down this this integral because this is always the most formal way the most formal way to write down a correlation function in the field theory language from string perturbation theory.
Yeah,
So
exactly. I was actually having something like this in mind. If you can find on this to reproduce it from the kind of vertex computation, like you say, from the I epsilon extended, which would be
yeah, that would be interesting. I think a natural thought is for example for what Bach have for what Bach have done in his 90s paper. We usually treat this Euclidean path integral by writing the propagator as a ghost field B divided by the L naught, where the L naught is a sum of is a power in the sum of the trace of the Q to L0 and the Q bar to L0 bar, right? And the propagator was defined in the way that B naught divided by L naught. It's also available if you just do the just redefine this propagator as a B0, the ghost field, divided by L0 plus I epsilon, and that will reproduce the same the same diagram that in this way. Well, in that way, the Q behave the same as the spiral line when you introduce B0 divided by L0 plus I epsilon in this part.
which would find exactly find the consistent extension for this Lorentzian epsilon vertex operator, the wall tree. Yeah.
Yeah, I agree that would be very interesting. Yeah, but I know very little about string field theory itself. Yeah, thank you for your question.
Yeah.
And another thing,
Thanks.
and you mentioned the tau to tau plus 2. Yeah, and that's because you for the specific case that back to here. For the specific case for the cylinder, you can see that let's just consider the easiest 2-point case. But 2-point case, you can the only possible non-planar for 2-point case is just the 1 point are in the outer perimeter and 1 is in the inner perimeter, right? And if you do the transformation tau to tau plus 2, because if you take a if you now take just a t transformation for tau to tau plus 1, you get a e to pi I e to pi I for times this insertion 1 and insertion 2, and you need to have tau to tau plus 2 for example the 1 over eta to 24. You have what tau to tau plus 2, you will get this 1 2 to 2 1 and then to and then back to 1 2 in your insertions. That doesn't make sorry I cannot connect. Yeah, my pad is a bit yeah, I cannot write down something right now, but
Yeah, Right. I see your point anyway. Yeah. Okay. Very good. Yeah. Thanks. Any other questions? Okay. If not, then let's thank the speaker again.